All right, guys, let's take a look at 8, 9, and 10. 8 is the multiplication rule for non-independent events. So this tells us that the probability of A and B is equal to the probability of A, times the probability of B given A. Or you can also do probability of B. Actually, let's back that up a little bit. All right. Describe two ways to determine if two events are independent. Sorry, I dropped the marker. I hope you're still with me. Okay. Two ways to determine if two. This is really asking us to take one formula and write it two different ways. We can check to see if the probability of A is equivalent to the probability of A given B. Or we can check to see if the probability of B is equal to the probability of B given A. And this will make more sense when we get down to some of these in the bottom. But what this is basically saying is you can pick something from everybody, like chances somebody has blonde hair in the school. Or you can narrow it down. Chances somebody has blonde hair of all the 10th graders. Well, if you just focus on the 10th grade class and you get the same probability, you get the same percentage, that lets you know that the grade you're in and whether or not you have blonde hair are independent. They don't affect each other. But let's say we were picking jewelry, right? The chances of picking somebody in the school that have jewelry is far less than the chances of picking somebody in the school with jewelry if you narrowed it down to the girls. Obviously, some girls do not wear jewelry, and also some boys like wearing jewelry. However, I bet you if you narrowed it down to the girls, your chances of picking somebody wearing jewelry are going to go up. What that lets us know is that jewelry and gender are not independent, right? Focusing on a gender might affect the chances that somebody is wearing jewelry. That idea is just what each of these two formulas is expressing. That it's independent if your probability overall is equivalent to your probability when you narrow it down to a smaller group. Let's work through number 10 to see some of that in examples. First few are just like our two-way frequency table earlier. Probability that you're female. Well, we got 2,294 females. And our total people is 8,253. Probability that you're under 65. Well, the probability that we have a lot of people under 7,632 people under 65. And once again, we're not told to narrow it down, so we always know we use the biggest total, 8,253. Probability that you're female and under 65. Well, we could use this rule, but we've got a table, so let's just check that. Here are females, here are people under 65. There's a small group right here, 2,259 out of 8,253. Explain how the values in A, B, and C prove if the events are mutually exclusive or not. Well, if they were mutually exclusive, nobody would belong to both categories. However, as we can see, there are some people that are female and 65. In other words, because the probability of F and 65 does not equal 0, right? If there were 0 people in that overlap, we'd be able to prove if these events are mutually exclusive. Okay. Now, we know they're not mutually exclusive. There's some overlap. Let's check to see if they're independent. That's a slightly different thing. When we do E and F, we can go back and check independence. So E says the probability that you're female if we narrow it down to people under 65. So let's look. How many people are under 65? 7,632. That's our new denominator. Of those, how many are female? 2,259. Let's finish up F. Probability that you're under 65 if you're female. So now we're narrowing it down to the females. We're narrowing it down to those 2,294 people. So we're looking at a row. And in that row, how many are also under 65? 2,259. So I want to ask a separate question that isn't in this particular problem, right? Oh no, I'm sorry, it's part G. So we're going to go ahead and do part G right now. I know you can't see it on the screen, but G says, do the values in part E and F along with what we've done in A, B, and C. Prove if the events are independent or not. Well, look, many fractions aren't the same. 1 over 2 does not look like 5 over 10. They're different numbers. But we know that they're equal because if we divide them, they are both 0.5. So let's check. What's the chances that you're a female? Well, if we actually divide those, what we get is answer A is equivalent to 0.2779, or 28% chance that you're female. Well, if we narrow it down to people that are under 65, and we do 2259 divided by 7632, answer E, if we converted it to a decimal, we get 2959. Or what we get is a 29 to 30% chance. Look, this is around 28%. This is around 30%. That's a slight difference. But what it means is the chances of picking a female at random are about 28%. If we narrow that down to people under 65, our chances go a little higher. We have about a 30% chance. We have a slightly better chance. So the age that you are affects the probability that you're female in this table. Being under 65 or being over 65 affects the probability. It gives you a slight increase in probability if you're under 65. So that lets us know that gender and age in this, or we should really say being female. Female and age are not independent. They have an effect. Your age seems to affect the probability you're female a little bit. All right, I kind of ran out of room, sorry about that. But that's G, so actually now we've done with 3 pages. Click on the next video for number 11.